Very, very good morning, dear lovely students. How are you doing? Good morning, good morning, good morning. I hope you are doing well, as well as revising all the concepts that we are studying in the class. Okay. So in the last class, we have studied about geometrical isomerism, the cis-trans isomerism majorly, that cis isomer versus trans isomer when we compare. Cis has more boiling point, trans has more stability, cis has more polarity, cis has more, good morning, Niharika. Cis has more heat of hydrogenation, trans has more stability, and these things we have studied in the last class. Okay, so trans has more melting point as well. Today, good morning, Chandana. This is going to be most probably the last class of isomerism. In case anything is left, we'll take one more. Today we'll be talking about geometrical isomerism, the last part, which is E and Z nomenclature. Good morning, Anil Kumar. How are you, everybody? Chandana, how are you? Niharika, how are you? Anil, how are you? How is everybody doing? Where are you guys from? Can you tell me your native places? Niharika, Chandana, Anil, can you tell me your native places? So by the time you reply, I'll be just dealing with the next topic, which is going to be EZ nomenclature. Okay. So let's start with EZ nomenclature and then we'll talk about optical isomerism today. So our concept for today, topics for today are going to be EZ nomenclature, and then we'll talk about optical isomerism. In optical isomerism, our main topic will be how to check RS configuration, what are enantiomers, what are diastereomers, and what are mesocompounds, and what are racemic mixtures. This is what optical isomerism consists of. Hi, so yeah, I've got the replies. Malur, Anantpur, Hyderabad. Okay, Charan is okay, and gaming. This is from Vijayawada. All right. So nice to meet you all. Nice to talk to all of you. Okay, once you come and join, we'll be able to meet as well. Hi, Jay Surya. I am from Haryana, basically. Okay. My name is Anirudh. In case anybody does not know till now, my name is Anirudh Mehta. Okay. So I hope to meet you all soon, very, very soon. InfoSpace, Anudeep. Chandana says, my shoulder pain is still there, but it is kind of less. I'm having some painkiller, so I'm able to move a bit. Okay. So all these things we'll keep on talking about. Actually, my shoulder has a problem for last 2 years, but I'm not able to go for a surgery because that requires a little bit of rest. So it comes and goes. Within 3 months, if I do some kind of a workout or something, I start getting the pain again. So I played some badminton a few days back. That's why the pain has reoccurred. So it's like this. So today's topic are going to be these ones. I am sure all of you are very scared of RS nomenclature. All of you are scared of the optical isomerism overall. Okay. I can promise you that listen carefully. I'll be going slow only. After 2 classes, all your fear of optical isomerism should go away. Overall, in any isomerism should go away automatically. Okay. So EZ nomenclature, beta, very simple. Whenever you have a carbon double bond carbon or you have a ring, and on the ring or on the carbon double bond carbon, all 4 groups are different. A, B, P, Q, something like that. When all the groups are different, in that case, cis-trans will not be named as, because there is no same group. We'll say EZ. How to say EZ? We'll be using a rule called as CIP rule, Kahn-Ingold-Prelog rule. Using CIP rules, Kahn-Ingold Prelog rules, we will rank the groups on both carbon. On both carbons, we'll rank the group. So let's say A versus B, there is a fight between A and B. If A wins, I say A, you are rank 1. Between P and Q, if P wins, I'll say P, you are rank 1. If rank 1s are coming on same side, which looks like a cis, will be Z isomer. Okay, remember. Z isomer. So the one who looks like a cis is a Z. Cis was same group on same side. Here same rank on same side. If same rank is on same side, we'll call it as Z. Okay. You can remember it as sizzler. Okay. To learn it, to remember it, I'm just saying cis-like is Z. Sizzler. Okay. Sizzler all of you have heard about. So sizzler. Cis is Z. Same way, if here A was the winner and here if beta was the winner, if one and one are opposite side, it is going to be E isomer. Okay. So trans-like is E, cis-like is Z. Now the only condition left is what is that CIP rule? CIP rules are actually beta set of 4 to 5 rules. Set of 4 to 5 rules. Always follow them line by line. Do not skip. Okay, always follow them line by line. So the name is CIP rules. Kahn-Ingold Prelog rule. No need to write anything like this here. Just need to practice few examples. Now, how to decide the rules? I'll just tell you the rules in a short form. You can just write them as it is. CIP rules in short. First one is atomic number rule. Atomic number. Yes, correct Niharika. Atomic number rule. First one is atomic number rule. So what you have to do is you have to check the atomic number of directly attached atom to the sp2 carbon. Atomic number of directly attached atom. So atomic number of directly attached atom is directly proportional to priority. That is the first rule. 90% of the questions will be able to do by the first rule only. Okay, 90% of the questions can be done by the first rule only. For example, if I have a chlorine here, I'll just write it here. If I have a chlorine here, if I have a CH3 here, if I have a hydrogen here, and if I have a NH2 here. Okay, so the rule says that on this carbon, these two are fighting. Chlorine is fighting with nitrogen, not NH2, nitrogen. So the directly attached atom is chlorine versus nitrogen. Chlorine has more atomic number, so chlorine becomes the winner. Chlorine becomes the winner. Atomic number we have to see. Carbon versus hydrogen. Carbon is the directly attached atom having higher atomic number. So both the ones are on the same side. So it is cis-like, which is Z. Which is Z. Okay, like this. If atomic number rule does not work, then go for mass number rule. Mass number rule. Only if rule 1 fails. Only if rule 1 fails. Okay. If rule 1 fails, then we go for mass number rule, which is mass number A of the directly attached atom. Directly attached atom is directly proportional to priority. Only if rule 1 fails, then you go for this one. For example, if I have carbon double bond carbon, here hydrogen, here deuterium, here CH3 with a carbon 14, and here COOH. Can you all tell me whether it is E or Z? Can you tell me whether it is E or Z? Everybody, practice, try this. Can you tell me whether it is E or Z? Everybody, quickly like the video. Those who are starting to attend the class. 17 people are there watching. 3 likes, very poor. Poor performance by me. You can like the video, move ahead and tell me the answer of this one. Whether it is E or Z according to you. Tell me. Whether it is E or Z according to you. Vijayawada Mahindra, Vijayawada. Can you tell me E or Z here? Everybody? Okay, E isomer, that's good. That's correct, everybody. So here, carbon 14 is fighting with carbon 12. Normal carbon is carbon 12, we know. So this is carbon 14, which will have more mass numbers. So this is rank 1 here on the top. Here, hydrogen deuterium atomic number is same 1, 1. So we go for the second rule, where deuterium will be mass number 2. Mass number 2, so it is more prior. So 1 and 1 rank are coming opposite. So it is trans-like, which is going to be E isomer. Like this we have to tell. Okay. So E and Z have some full forms also, not very much required. Z is called as Zusamen. E is called as Entgen. Okay, I'll show you the spelling and everything, but not much required. Zusamen and Entgen. Next one. If rule 2 also fails, atomic number same, mass number also same, then go for Chipko rule. The name is given just by me, just normally to make you remember. Chipko rule means if the first atom is not able to decide, check the directly attached next atom. So ask to that person that who is directly attached to you, what is the best option next to you, that will decide. So check the atomic number and mass number of next attached atom. Check the atomic number and mass number of next attached atom. If the directly attached atom is not able to decide, check next. For example, if I have like this, C double bond C, here CH2Cl, here CF3, here COOH, here CH2Cl. Or let's take, just take NH2 here. Okay, let's say we have to check for this particular compound. Now, on the left hand side, so it's simple. Carbon versus nitrogen. Nitrogen says, I am more atomic number, so I am the winner. Nitrogen atomic number is more, it is 7. Carbon is 6. Nitrogen is the winner. But on the right hand side, carbon versus carbon, there is a tie. Carbon versus carbon, there is a tie. So rule 1 failed, rule 2 failed. Mass number same, atomic number also same. Now you ask carbon, who is next to you? This carbon will not say hydrogen is next to me, no. Because if you say hydrogen is next to me, you will to lose. So always show your best card first. Always show your best person. So we ask carbon, who are you directly attached to? He says, I am attached to chlorine, hydrogen, hydrogen. He is attached to fluorine, fluorine, fluorine. One by one, you have to check the rule. So when you ask this carbon, he will say, I am attached to chlorine. My best card is chlorine. This carbon says, my best card is fluorine. So obviously, chlorine is better. So I'll get rank 1 on the top here. So 1 top, 1 bottom, it is E isomer. E isomer. Okay. Chipko rule. If the rule does not work for the first atom, check the next best atom. Don't say I have a hydrogen. Nobody cares about hydrogen. Always show your best card. So this is about your rule 3, Chipko rule. Sometimes rule 3 will also fail. Very, very few times. This is very rare to check. In that case, you have to check the duplicacy-triplicacy rule. Duplicacy-triplicacy, which means that whenever you have a double bond, A double bond B, you can consider that A is attached to two B's. You can consider that A is attached to two B's. That's what we are trying to say. So, whenever we have, so duplicacy-triplicacy means duplicate a double bond, triplicate a triple bond. Okay, this means that if I have a A double bond B, it will be considered as A attached to two B's and B attached to two A's. Okay, duplicate. A double bond B means A is attached to two separate B's. B double bond A means B is attached to two separate A's. So you can open it as like this. A attached to two B's, B attached to two A's, one here, one there. This is how you duplicate it. Okay. When to use it? It's easy only, you will be able to tell. If you have a P triple bond Q, that means that you will consider it as P attached to three Q's. Further, Q also attached to three P's. One P here, two more P. One P here, two more P. One P here, two more P. Like this. Triplicate the triple bond, duplicate the double bond. This is the meaning of duplicacy-triplicacy. Okay. When do we use it? Only in the rarest of the cases, when the functional group which is attached has a double or triple bond. Like that. Okay. You want to see one example? Let us see. All of you see here. One example of duplicacy-triplicacy. One example of duplicacy-triplicacy. See here, everybody. C double bond C. Here I have C triple bond CH. Here I have CH, CH3 whole twice. Here I have CHO. Here I have CH2OH. Okay. After I explain this question to you, quickly tell me whether it is clear to you or not after the explanation, and then I'll give you one or two questions to do, and that completes our EZ. So, here I'm just opening everything. All of you can see here. Let's see left side. This is a carbon. Okay. This is a aldehyde. Aldehyde means C double bond OH. So this carbon is attached to two separate O's, I can think, and one hydrogen, because this is C double bond OH. Okay. So this carbon is not attached to one oxygen, it is actually attached to two oxygens. On this side, it is CH2OH, means this carbon is attached to two hydrogens and one OH, which is alcohol. Correct? This is how I can open it. This is C double bond O, and a H, aldehyde. So carbon is attached to one hydrogen and two separate oxygens. Because if I think of it like this, then I can't decide. If I think of it like this, now I cannot decide. This carbon is also attached to oxygen. This carbon is also attached to oxygen. This carbon also has a hydrogen. This carbon also has a hydrogen. So I can't decide. So we have to remember the rule of duplicacy-triplicacy, that double bond O can be considered as two separate O's. Now I can easily decide. This carbon says I have oxygen. This carbon says I also have oxygen. There is a tie. What else do you have? I have one more oxygen. Oh, you are the winner. I don't have any more oxygen. Rank 1. Okay, rank 1. This side, C triple bond H means this carbon is attached to three more carbons. One carbon, two carbon, three carbon. This is what it is, a carbon attached to a hydrogen and two CH3 groups. CH3, CH3. So we start by checking. I am a carbon. I am also a carbon. What is attached to you? I am attached to a carbon. I am also attached to a carbon. What else? I am attached to another carbon. I am also attached to another carbon. Till now there is a tie. What else? I am attached to another carbon. Okay, now I am attached to hydrogen. So top one is the winner. It is attached to carbon 3 times. First one, carbon, carbon, tie. Second one, carbon, carbon, tie. Third one, carbon, hydrogen. So the winner is the top one. 1 and 1 on same side. It is Z isomer. Is it clear to everyone? Yes or no? Quickly tell me. Are the 4 rules up to duplicacy, triplicacy clear to everyone? Please tell me. If it is clear, then we'll move forward. Please tell quickly. Okay, Manideep. All right. So you can write it down, complete it. This is about the geometrical isomerism. This is the end of geometrical isomerism. Okay. Now we'll be moving towards the optical isomerism. We'll be moving towards the optical isomerism. I've told you all this thing. E and Z, you can check yourself now. This particular example, you can tell me. Write EZ for each. Quickly, quickly. I'll give you 2 minutes. I'll give you 1 minute. 1 minute is sufficient. Write EZ for all of them. Write EZ for all of them. First, second, third, fourth, all the answers in same message you can tell me. Carbon, fluorine, fluorine is the winner, rank 1. Oxygen, bromine, bromine is the winner, rank 1. 1, 1, Z. Here, nitrogen, nitrogen, same. This nitrogen says I am attached to oxygen. So rank 1 goes to the top nitrogen. Carbon, carbon, same. This carbon is attached to one more carbon, rank 1 on the top. This is also Z. Carbon, carbon, but this carbon is attached to one more carbon. Ethyl means CC. So this will be rank 1. Br is better than carbon. This is rank 1. This is also Z. Here if we come to carbon, carbon, same. This is double bond, means this is attached to 2 more carbons. This is attached to only 1 carbon. So the bottom one is winner, rank 1. This side, carbon, carbon, same. This carbon says I am attached to chlorine. This carbon says I am attached to carbon. So chlorine is the winner, rank 1. This is going to be E. So it is Z, 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 E. Correct, correct. Good. Moving ahead, optical isomerism. Optical isomerism. To study about what is optical isomerism, first we'll remember the definition. Correct, correct Niharika, correct Manideep. First thing we'll remember the definition. What are two optical isomers? The name itself tells you optical means something related to light. Something related to light. So what are optical isomers? Two compounds having same molecular formula, Same structure also, because they are stereoisomers, right? Same molecular formula, same structure, but they behave differently. They behave differently towards plane polarized light. That is what we call as optical isomer. If I have two compounds A and B, their formula is exactly the same. Structure is exactly the same. Okay. But when I pass plane polarized light through it during a polarimetry experiment, they behave with that light in a different manner. Maybe one rotates it, other does not rotate it. So one will be optically active isomer, one will be optically inactive isomer. Maybe one rotates it to the right side, one rotates it to the left side. One will be dextrorotatory, one will be levorotatory, like that. These are optical isomers. So what are optical isomers? Compounds with, write down, compounds with same molecular formula, same structure, but show different behavior towards plane polarized light. In polarimetry experiment. In polarimetry experiment. But one cannot be superimposed on the other. Niharika, not exactly true what you are trying to say. Okay, what you are trying to say is only valid for enantiomers. Okay, so optical isomerism occurs when substances have same molecular formula, same structure formula, but one cannot be superimposed on the other. Okay, one cannot be superimposed on the other. That is the condition for optical isomerism. You can say it is the condition for optical isomerism, but optical isomerism, what is the meaning? What is the definition? It is going to be the compounds which have same formula, same structure, but they behave differently towards the plane polarized light. Why they will behave differently is what you are telling. Okay, so reason you are telling, I am telling definition. That's correct. Whatever you are saying is a correct reason for it. We'll talk about it. Okay. Now, whenever we want to talk about optical isomerism, the very first thing we should talk about is chirality, which Niharika has said correctly. Chirality means non-superimposability of mirror image. Chirality means non-superimposability of mirror images. Okay. All the definitions will keep coming. Many of you get confused between chiral molecule versus chiral carbon. Both are very different terms. Okay. Please remember it that you are not required to have a chiral carbon for a molecule to become chiral. Sometimes molecule can become chiral even without having a chiral carbon. All those points will keep coming. Please see carefully. Okay, so chirality of a molecule means a molecule is such that its mirror image does not coincide on the real image. So the mirror image and the image do not super coincide. That is known as chirality. For example, the handedness also we say. Our right hand is like this, right hand is like this. When I put a mirror here, this is how my left hand looks like. So when I try to superimpose the left hand on right hand, they are not completely coinciding. The thumb is remaining outside. Correct? So this is called as chirality. Chirality of a molecule, chirality of an object. If I take this bottle, the mirror image of this bottle is going to look exactly like this. Okay? It is going to look exactly like this. Now you can see that I can exactly super coincide them. So this bottle is achiral. This bottle does not contain chirality. This bottle has exactly the same mirror image, so I am able to superimpose them. So this cannot show optical isomerism. This bottle cannot show optical isomerism. Okay, this is the way to check. Now don't keep the bottle like this and say, sir, now to its mirror image is achiral. Now to this mirror image is achiral. Correct or not? So you have to check from every end. Don't try to keep the bottle like this. Then you will say, sir, its mirror image looks like this. Now the cap on left side, cap on right side, they are not super coinciding. No, you have to check it from every side. In a molecule, you'll be able to do it without even checking the mirror images because there are some rules. Like a carbon should contain all 4 different groups, or the molecule should not have a plane of symmetry or center of symmetry. So you'll be able to check the chirality not by drawing the mirror image every time, but by just checking the symmetry elements, which is plane of symmetry and center of symmetry. Okay, all these things will be coming in few minutes. First, I'm just trying to explain to you in a layman language. So how to check the chirality of a molecule, you will see. Whenever you see a molecule, if you are able to cut the molecule into 2 equal halves using your hand, if you are able to cut the molecule into 2 equal halves using your hand, that molecule is going to be achiral, means it will not be chiral. So whenever a plane of symmetry is present, molecule is not chiral. So if I look at this bottle, I can cut this bottle into 2 equal halves by passing my hand like this. Even if it was kept like this, still I can cut it by passing my hand like this. Even if it was kept like this, I can still cut it by passing my hand like this. So whenever you look at a molecule, try to cut it into 2 equal halves. If you are able to cut it into 2 equal halves, it will become achiral. Okay. Then you might say, sir, if this is our hand, I can cut my hand from side like this and it will cut it into 2 equal halves. You are absolutely correct. But a hand, if I keep it like this, no, hand is a planar object. And according to any planarity, whenever there is a planarity, molecule has to be achiral. So books write it in a wrong way. Books should not say handedness. Books do not want to say our hand is chiral. Our hand is not chiral. I can cut it from the side like this and I can get 2 hands. Yes or no? If I take this bottle, if I cut it like this, I'll get 2 equal halves of the bottle. If I take my hand and I cut it like this, I'll get 2 equal parts of my hand. Yes or no? 1 part here, 1 part here. So hand is actually also not chiral, but yes, from looking from the front, it looks chiral. Now if I keep my hand like this, now see, from the side you see my hand like this. Now I can't cut into 2 equal halves. Now it has become a non-planar molecule. Now it became a non-planar molecule. Now my finger is pointing forward. There is no finger backward. So I can't cut it anyway. Now you can't cut it. Okay. If you look at it from the side, if I cut it like this, forward side 1 finger is there, backward side there is no finger. Now it is chiral. This is not chiral actually. It is a planar molecule. You can cut it like this. Okay. So planar molecule like benzene, like cis-butene, like trans-butene, they can never be chiral. Okay, by looking at a trans-butene, you might say, sir, this one to looks chiral. How will I cut it into 2 equal halves, sir? Sir, this one to is looking chiral to me. How will you cut it? Sir, I can't cut it like this. Here CH3, here H. Sir, I can't cut it like this. Here H, here CH3. Yes or no? So by looking at a trans-butene, you might feel it is chiral, but it can't be chiral because it's a planar molecule, beta. It's a planar molecule. And whenever a molecule is planar, it always carries something called as molecular plane of symmetry. Planar molecules always carry molecular plane of symmetry. Molecular plane of symmetry is present, which you can also call it as slice plane of symmetry. You can always slice a planar molecule into 2 equal halves. Slice it from the side, from the cross section, you can slice it. I hope this is clear, and this is very important point where most of you do mistake. So a planar molecule is always going to be achiral. A planar molecule is always going to be achiral because it will have a slice plane of symmetry. Okay, slice plane of symmetry. So let us start. What is chirality? To go for chirality, first we should know what is a chiral carbon or chiral center. No need to write the definition. You can just remember a carbon having a sp3 carbon, first of all, having all four different groups attached to it. A sp3 carbon, it is a sp3 carbon having all four different groups attached to it. A, E, let's say B is coming front of the board, D is going behind the board. This is called as a chiral carbon. Okay, chiral carbon is one of the condition which might be required for chiral molecule, but it is not a necessary condition. Okay, so you can write this note point also. A chiral carbon is not the necessary condition to make a molecule chiral. Okay, having a chiral carbon is not the necessity to make a molecule chiral. Many times when there are 2-3 chiral carbons present, still molecule can be not chiral. When there are 2-3 chiral carbons present, still the molecule can be achiral or not chiral. Same way, there are few molecules which are chiral molecules, but they do not contain any chiral carbon. So remember it. Having a chiral carbon does not necessarily mean that molecule will be chiral. No. If there are 2 chiral carbons, there might be any plane of symmetry which can make the molecule achiral. And there are few molecules which are chiral but still do not contain any carbon which is sp3 and 4 different groups. Okay, both the sentences are correct. Can you have a chiral molecule without a chiral carbon? Answer is yes. Okay. Can we have a chiral molecule? Can we have a chiral molecule without chiral carbon? Answer is yes. We will see the example. Okay, 2 examples will come here, allenes and biphenyls. Allenes and biphenyls are some compounds which do not carry a chiral carbon, but still molecule is chiral. Then the question is, can a molecule having chiral carbons be a chiral molecule? Answer is again yes. So there is a possibility that molecule has chiral carbon, but still the molecule is achiral. This is also possible. Okay, both examples also will come as the class continues. Something you should remember. So what is a chiral carbon? A sp3 carbon attached to 4 different groups. Okay, so let us start. So these are things I have already told you. These are some examples. So this is lactic acid, a 3-carbon compound which is 2-hydroxypropanoic acid. It is a chiral carboxylic acid. Why it is chiral? Because you can see here this is 1 carbon which is a chiral carbon attached to a OH, CH3, H and COOH. So this is a chiral carbon. Whenever chiral carbon is only 1 in the molecule, whenever the chiral carbon is only one chiral carbon, molecule is 100% going to be chiral. Molecule is 100% going to be chiral. This is the third note point you can mention. So 3 note points I have told you. Note point 1 was molecule can be chiral without a chiral carbon. Molecule can be achiral with chiral carbons. But whenever a molecule has only 1 chiral carbon, only one, then it can never be achiral. It has to be a chiral molecule. So note point 3 we can mention a compound or a molecule with only 1 chiral carbon is always chiral. Is always chiral. A compound with only one chiral carbon is always going to be chiral. Is always going to be chiral. For example, look at this lactic acid. So this is the lactic acid. If you look at it in a tetrahedral structure way also, there is a CH3 on the top, there is a COH at the bottom here, there is a OH on this side, there is a H on this side. If I keep a mirror here, because all the four groups are different, okay, because all the four groups are different, whenever you keep a mirror next to it, its mirror image will never coincide. Obviously, while keeping a mirror, head and foot always remain the same, but left and right hand will change. So this H goes to the right side, OH comes to the left side. Okay, so if I try to superimpose them, you will see that they are not going to have a superimposability. So these are non-superimposable mirror images, which makes it a chiral molecule, optically active molecule. But whenever you don't have a chiral carbon, let's say I take this particular compound, which is going to be a 2-methyl propanoic acid. Now can you see these two groups are same? That means it does not carry a chiral carbon. It does not carry a chiral carbon. So if I draw it in a tetrahedral manner, I can think that two CH3 groups are the hands, let's say. On the top we have, let's say, a hydrogen, and at the bottom we have a COH. I can think of it like this. Okay, I can think of it like this. Now this molecule is same as this molecule, because in a tetrahedral all the bonds are 109 degrees, so I can consider it like this or like this. Now it does not carry a chiral carbon, so when I make a mirror image, head will remain head, foot will remain foot. If right and left hands are also same, then they are going to superimpose. They are going to superimpose. Can you see here? So whenever a carbon has at least two identical groups, you can keep one group on this side, one group on this side, and the molecule always become a chiral. You can cut it from the center like this. Let's say on the top I have hydrogen, at the bottom I have COH, but this is methyl, this is also methyl. You can always cut it like this. If you cut it like this, half hydrogen here, half hydrogen here, half COH here, half COH here. One methyl this side, one methyl this side. You can cut it like this. Okay. So by looking at the molecule like this, don't think it is chiral, sir. How will I cut it? You can cut it. Think of it in this way and then cut it. So when it is mentioned like this on the notebook, you might get confused, sir. I am not able to cut into two equal halves. You can cut. Keep the two methyls like this in the Fisher projection. Same way here, two hydrogens are there. I can cut it like this. I can still cut it like this. So plane of symmetry is present. These are optically inactive and achiral molecules and do not carry a chiral carbon as well. Okay. So this is what the chirality means. So chiral carbon means. So can you tell me among these, which of the following contain a asymmetric carbon atom? Asymmetric carbon atom means chiral carbon atom. Who contains a chiral carbon? Who contains a chiral carbon? Who contains a chiral carbon? And another question I'm writing here, question number 2. How many chiral carbons are present in following compound? How many chiral carbons are present in the following compound? Okay, Chandana Shri says D. D. In the A first we'll check. This carbon carry 2 hydrogen, can't be chiral. This carbon carry 2 hydrogen, cannot be chiral. So 100% both are not chiral. In this case, hydrogen, hydrogen same. In this case, chlorine, chlorine same. It can't be chiral. Both are achiral. In this case, hydrogen, hydrogen. In this case, also hydrogen, hydrogen. There is no chiral carbon. In this case, hydrogen, hydrogen. So this is the not chiral. This left carbon is the not chiral. But the right carbon contain a CH3 group, a H group, a OH group, and another fourth different group. So this second carbon, in this case, becomes chiral carbon. This contains a chiral carbon. Since the chiral carbon is only one, molecule must be chiral molecule. It is a chiral molecule as well. Chiral molecule as well. Molecule is chiral. Carbon is chiral, molecule is also chiral because there is only one chiral carbon. Others are achiral molecule. Can you look at this molecule and tell me how many chiral carbons are there, Niharika and Chandana? How many chiral carbons in this molecule? Whenever you see a chiral carbon, always put a star there. Okay? Put a star there whenever you see a chiral carbon. Can you tell me how many chiral carbons are present in this molecule? Manideep says 3. 1, 2, 3. Anybody else? Or should we lock in at 3? Two. Niharika says 2. Okay, let us see. See, this is the sp2 carbon. So sp2 carbon can never be chiral. This is also sp2. It is sp3, but it has 2 hydrogens. So this cannot be chiral. This is sp3. It has 1 hydrogen, 1 NH2. On this side, a different group. On this side, a different group. Okay. Overall group you have to see. Don't say, sir, it has a CH to this side, CH to this side. No. On this carbon, on this yellow carbon that I am showing here, on this carbon, right hand side there is a CH to CH. On the left hand side there is a CH to CH double bond. So obviously these are two different groups. So this carbon is actually chiral. This carbon is chiral. Then next carbon has 2 hydrogens, so it cannot be chiral. Next carbon also has 4 different groups. You see here, 1 hydrogen, 1 bulky group, one this CH to CH2, one is CBr. So yes, all 4 groups are different here. So this is also going to be chiral. This is also going to be chiral. This is also going to be chiral. Now, next one. This is CH2. So 2 hydrogens are there. Obviously, it is not chiral. 2 hydrogens are there. Obviously, it is not chiral. Next one is also chiral. You see here, this one. It carries 1 hydrogen, 1 chlorine, 1 this group, 1 that group. Both are completely different groups. So this is also going to be a chiral carbon. This is also going to be a chiral carbon. Next carbon. This carbon carries 2 CH3s. So obviously it is not chiral because it carries 2 same groups, CH3, CH3. And the final CH3, CH3 are also not going to be chiral. So there are 3 chiral carbons present in it. 3 chiral carbons are present in it. Okay. So this is the one. So 3 stereo centers are present here. How many stereo centers are present? 3 stereo centers are present here. So this is what we can talk about. Moving to the next one. So can you tell me which of the following molecule is not chiral molecule? Not chiral molecule. Which is a not chiral molecule? Can you tell me? I told you to check the chirality of a molecule. Try to pass your hand through it and try to cut it into two equal halves. Try to cut it into two equal halves. Or just tell me which is, maybe both of them might be not chiral because I did not take all the four options here. I've taken only two options here. Just tell me which is chiral, which is not chiral. Which of the following is chiral or achiral? Okay. You can wait for some time because this will require the center of symmetry. I have not told you what is center of symmetry till now. This question can be done later. Okay. This actually has a center of symmetry. Okay. COS is present, center of symmetry. We have not talked about the symmetry elements yet. So we'll wait for some time. We'll do this question at the end. At end we will do. Okay. So now, when it comes to looking at a chiral carbon, each chiral carbon will have some configuration. Like in the geometrical isomerism, you have seen the configuration cis-trans, EZ. Here the configuration will be either, we'll call it as absolute configuration or relative configuration. To check the configuration, we have to use two types of projection, wedge dash projection and Fisher projection. Okay, wedge dash projection and Fisher projection. A wedge dash means a tetrahedral is mentioned like this, where they have given two bonds on the plane, one bond coming out of the plane, one bond going behind the plane. This is wedge dash, A, B, C, D. This is a chiral carbon. This is wedge dash projection. We must be very good at converting it to a Fisher projection, which looks like a 2D projection, like a plus. Okay. Once we convert it to Fisher projection, we can check for the configuration, which is going to be R or S configuration. So let us talk about the main important part here, which is going to be, write down, absolute configuration. Absolute configuration at any chiral carbon. This is most important topic for NEET. And most of you do mistake here. I'll give you a trick. I'll give you a trick so that you never do any mistake. I'll give you a trick so that you never do any mistake in finding the absolute configuration. Absolute configuration are of two types, R and S. How to find the absolute configuration? Step 1. Always convert wedge dash to Fisher projection. That is the first thing. Main trick lies here only. Okay, you don't have to imagine the compound. You don't have to listen to what book says. Books will tell you different ways, but you will mostly do mistake in those cases. I'll give you a simple trick. First thing is convert wedge dash to Fisher projection. How to convert? Please remember, whenever you see a wedge dash can be written in four ways. One way is this. One way is this. One way is this. And one way is this. Four ways to write wedge dash. Books will give wedge dash in four different methods. One is wedge and dash are on left and right. Okay, this is the first one. Trick 1 applies here. Wedge dash on left hand side or right hand side. So you can see here, wedge dash are on right here, wedge dash are on left here. This is the second way where they'll give wedge and dash on top or bottom. Okay. Simple trick I'll tell you. Whenever wedge and dash are given on left hand side or right hand side, then the trick is move wedge bond. Move wedge bond. I'll tell you what is the meaning. And whenever wedge and dash are given on the top or bottom, then move dash bond. Then trick is move dash bond. What do I mean by this? All of you carefully see here. All of you carefully see here. This is first step. I told you, convert wedge dash to Fisher. How to convert it to Fisher? I am telling you a trick for this. How to convert wedge dash to Fisher? I am telling you a trick for this. See here. So the first case is when wedge dash are given on the left or right. Let's say there are 4 groups present here. One is COH, one is hydrogen, one is OH, one is CH3. Okay. Here also 4 groups I'm mentioning. Let's say a NH2 here, a COOH here, a hydrogen here, a methyl here. You want to check the RH configuration. Step 1 says convert it to Fisher projection. What to do? Please see here, everybody. As soon as you see the wedge dash are given on the sides, right or left, move the wedge bond. So wedge was on left hand side, just take it to right hand side. Just take it to right hand side. Just say OH, you open up here between COH and H. So I have moved the wedge bond between the 2 bonds which were on the notebook. COH was on the notebook, hydrogen was on the notebook. I just moved the OH in between COH and H. So this is how it will look like. So convert it to Fisher. Fisher looks like this, a plus, where OH has gone to right hand side. In between COH and H, in between COH and H, CH3 still remained on left. This is as simple as it can get. No other simplest way you can have. Again, I'm telling. Move the wedge bond and take it between the 2 bonds which were on the notebook. On the notebook, COH and H were sitting. I took the wedge OH and opened it between those 2. This is the Fisher projection. This is the Fisher projection. Let's do the second one. Okay. In the second one, who will move? The wedge will move. Who is wedge? COH. So take your COH, open it between NH2 and CH3. So make a plus. COH moves here between NH2 and CH3. Between NH2 and CH3. And H remained on left hand side only. H remained on left hand side only. Simple. Correct. This is how you convert wedge dash to Fisher. Here opposite to do. Let's keep a COH here. Let's keep a H here. Let's keep a CH3 here. Let's keep a bromine here. Let's keep a NO2 here. Let's keep a H here. Let's keep a OH here and iodine here. Yes. So here opposite, whenever wedge and dash you see are on the top written or bottom written, then dash will move, dash. So bring COH in between these 2. COH was on the top, I have brought it at bottom. Make a plus. COH you come to bottom. You come between methyl and bromine. Between methyl and bromine. H remains there wherever it was on top, H remains on top. And in the second one, who will move beta? OH will move. I told you the trick. OH is the dash. Move it between NO2 and H. So H was here, NO2 was here. I didn't change them. Iodine was at bottom. I didn't change it. I just brought the OH on the top. Is this trick clear to everyone? Is the step 1 clear? Trick clear to everyone? Yes or no? Is the trick clear to everybody? Once you have done this step 1, rest of the steps are very, very easy. Rest of the steps are very, very easy. Step 2 is Rank all the 4 groups using CIP rule. CIP rule already we have done in the EZ nomenclature. So step 2, rank all 4 different groups using CIP rules. Rank all 4 groups using CIP rules. So let's rank them and write the next rule as well. Step 3. Move from rank 1 to rank 2 to rank 3. Move from rank 1 to rank 2 to rank 3. 1 to 2, 2 to 3 we have to move. Move from rank 1 to rank 2, rank 2 to rank 3. When you move in this fashion, you will be able to decide R and S. When you move from 1 to 2 to 3, last step, step 4. If rank 4 is vertical or if rank 4 is horizontal, okay, when you are moving from 1 to 2 to 3, see where is rank 4. If rank 4 is on vertical line, here, either here or here, then clockwise will be R, anti-clockwise will be S. Clockwise will be R, anti-clockwise will be S. But if 4th group is horizontal, reverse. If 4th group is coming on this line, horizontal line, then clockwise will be S, anti-clockwise will be R. Okay, simple. Okay, after doing the step 2, rank all 4 groups using CIP rules. CIP rules we just did, no, atomic number, mass number, Chipko rule, duplicacy, triplicacy. After we have done all the 4 ranking, rank 1, rank 2, rank 3, rank 4. After doing all the ranking, we'll move from 1 to 2 to 3. I'll show you the example. While moving from 1 to 2, 2 to 3, if 4th group is vertical, if you are moving clockwise, it is R. If you are moving anti-clockwise, it is S. But if 4th group is on the horizontal line, then if you are moving clockwise, it becomes S, anti becomes R. Okay, see here, everybody. First example I am showing. I am using the CIP rules. Carbon, carbon, oxygen, hydrogen. Oxygen become rank 1. Carbon, carbon, tie. Chipko rule. I am attached to oxygen becomes rank 2. This carbon becomes rank 3. Hydrogen becomes rank 4. 4th is vertical. So we have to follow this rule. 4th is vertical. Go from 1 to 2, 2 to 3. Where is 1 here? Where is 2 here? Where is 3 here? So 1 to 2, 2 to 3. We are moving anti-clockwise. We are moving what? Anti-clockwise. 1 to 2, 2 to 3. Anti. 4th vertical. Anti is S. So this is S configuration. This is S configuration. Okay, I'll just write here. It is a S configuration. Next one. Let's rank first. Carbon, carbon, hydrogen, nitrogen. Nitrogen gets the rank 1. This carbon is attached to oxygen, gets rank 2. This carbon is attached to hydrogen, gets rank 3. Hydrogen gets rank 4. 4th is horizontal. These rules I have to follow. Let's go from 1 to 2, 2 to 3. Again we are moving anti-clockwise. Again we are moving anti-clockwise. But now anti-clockwise will be R. Now anti-clockwise will be R because 4th is horizontal. 4th is horizontal, anti-clockwise will become R. Okay, simple. You remember the vertical one, horizontal is reverse of it. Another example you can see here. Bromine gets rank 1. Carbon with oxygen gets rank 2. Carbon gets rank 3. Hydrogen gets rank 4. We have to move from 1 to 2, 2 to 3. Clockwise we are moving. Clockwise. Clockwise. Where is fourth? Fourth is vertical. Clockwise means R. So this is R. Now I want you to tell me the last one. Those who are listening to the class, tell me the last one. Whether it is R or S, the last one. Dharmarao Gorja says S. Mahindra says S. Okay, let us see. So rank 1 goes to iodine because iodine is highest atomic number. Rank 2 goes to oxygen because oxygen is second. Nitrogen, then third. Fourth will be hydrogen. We have to go from 1 to 2, then to 3. So 1 to 2, 2 to 3. We are moving clockwise. We are moving clockwise. And where is the fourth group? It is horizontal. So clockwise will become S. So yes, very good. Clap for yourself. You have got it correct. Is it clear to everybody? Has it made it simple? If this trick has made it simple, just write a simple in the chat box. If you learned something new today and it became simple for you, just write a simple in the chat box. Maximum times in NEET question come from finding the RS configuration also. So what did we study today? That whenever there is a chiral carbon, on each chiral carbon you can write a RS configuration. A chiral carbon does not guarantee you the chirality of a molecule. But whenever there is one chiral carbon, there is always going to be a chiral molecule. When there are 2 chiral, 3 chiral, 4 chiral, we don't know, we have to check. We might be able to cut it into 2 equal halves. So molecule can be achiral even if it has many chiral carbons. So these are the things we have studied today, and so we'll try to keep it till here, because after this we have all this we have studied already, how to convert to Fisher projection. So all the rest of the definition, what is enantiomerism, what is diastereomerism, all this we'll be doing in the next class. Okay, all this we'll be doing in the next class. We'll keep this class here so that we have finished up to R and S configuration. I'll give you 2 questions to do right now. You can tell me the RS configuration in them. Tell me whether it is RS write the IUPAC nomenclature of this compound. IUPAC nomenclature of this compound by mentioning the RS. So whenever you write the IUPAC nomenclature of any optically active compound, you write it like this. Let's say this is R. So I'll call it as 2R butanol. I'll call it as 2R butanol. I'll call it as 2R, 3R, whatever. 2R, 3R, 2-hydroxy, 3-chloro, like that the name will be. So you tell me the IUPAC nomenclature of these two. Here also you tell me whether 2R, 3R, which type it is there. So it is first carbon, second carbon, third carbon, fourth carbon. Numbering of carbon according to IUPAC nomenclature. So I am asking, it is 2 what, Three options are there. Four options. 2R, 3R, 2R, 3S, 2S, 3S, or 2S, 3R. Choose the correct option here. And what is this? 2-butane-2-ol. Name it. Yes, what are we getting? First one, S. Yes, correct. Very good. All of you do it yourself. It is S is correct. What about the second one? This is second carbon. Write it separately. Okay, this is second carbon. I'm writing it separately. Third carbon, I'm writing it separately. Second carbon has a C and a O on the top, O at the bottom. Okay, see here everybody. This carbon is attached to carbon on the top, carbon at the bottom also. This carbon is attached to carbon on the top, carbon at the bottom. Top carbon has an oxygen. Bottom carbon has a chlorine. So this is a better carbon. Okay. On the right hand side, oxygen. On the left hand side, hydrogen. So rank 1 goes to oxygen. Rank 2 goes to a carbon carrying chlorine. Rank 2 goes to the carbon carrying chlorine. Rank 2 goes to the carbon carrying chlorine. Rank 3 goes to the carbon carrying oxygen. And rank 4 goes to hydrogen. So we'll move from 1 to 2, 2 to 3 clockwise. But fourth is horizontal. So it is S. Yes, 2S. Good. And the next one here on this carbon, on the third carbon. On the third carbon, bottom is a carbon, after carbon oxygen. Right is a chlorine. Top is a carbon with oxygen. Okay. So till now there is a tie. For this third carbon, it says on the top I have a carbon, my carbon is attached to oxygen. Bottom one also says my carbon is attached to oxygen. This carbon says I am attached to a carbon also. This carbon says, oh, then I am the loser, I am attached to a hydrogen. And this is a H. So rank 1 goes to chlorine itself. Rank 2 goes to carbon attached to oxygen and a carbon. Rank 3 goes to carbon attached to only oxygen. Rank 4 goes to hydrogen. 1 to 2, 2 to 3. We are going anti-clockwise. 1 to 2, 2 to 3 anti-clockwise. It will become a R because fourth is horizontal. So answer is S and R. Fourth option. S and R. Yes, 2S, 3R. 2S, 3R. 2,4-dihydroxy, 3R chloro, butanoic acid. Very good, Dharma Rao. I hope it is clear to everyone. We'll keep it till here. Thank you. Bye-bye. Please revise and come in the next class. We'll be completing the isomerism part. Bye-bye.